SwayamPrabha. Digital India. Educated India. SwayamPrabha. Digital India. Educated India.
Hello, let us have a look at a very important aspect of all airports called as the airport declared distances. These are distances available at an airport which are specified by every airport in the airport charts, and they are used by the mission planners and the flight crew to plan whether a particular airport is safe enough to operate by a particular aircraft. And then these are declared in the airport charts, which are publicly available online. So, here is an example of how a typical section of an airport chart looks like. So, when you see this word D in the center, it means the distances mentioned in this chart are declared distances. For example, this particular airport has, as you can see, there are 3 runways, 2 of them are parallel runways and one of them is an inclined runway, but they are not crossing. So, you have runway 9L and 27R, 9R and 27L. So, as an aircraft comes from the left hand side to the right hand side, there are these 2 parallel runways. Note that the distance mentioned is 8002 feet length and 150 feet width. For this runway, the declared length is only 4309 feet and the width is 100 feet, and for the inclined runway, which is 1230, the length is 6800 feet and the width of the runway is 150. TWR 206 is the frequency of the tower, and TDZE8 stands for touch zone Z elevation, touch zone elevation of 8 feet. So, this airport is located at 8 feet above mean sea level, and the elevation of the touch zone, which are these areas 1, 2, 3, these are the touch zones. The elevation of these is 8 feet, and over a distance of 300 meters it remains, the maximum altitude remains 8 meters. And then there are so many other symbols which are there to communicate. There is an indication here that the following, these taxiway system is not in operation, so it has been crossed out, etc., etc. Now, before we undertake the declaration of distances, we should have a quick look at what exactly is the meaning or the definition of takeoff and landing, etc. So, takeoff in aviation is defined as ground roll plus transition distance plus climb distance, climb to an obstacle height. So, when you are at rest, you start rolling, which means you start accelerating till you reach a point where now you can lift off or you can leave the ground after the pilot initiates rotation. After that, you are going to slowly transition and go into a climb till you clear the obstacle height. The obstacle height is defined as 50 feet for a civil aircraft. So, the takeoff ground roll or takeoff ground run is from the start when the speed is 0 or the aircraft is stationary till the point where the aircraft leaves the ground or the main wheels of the aircraft leave the ground after rotation. That is takeoff ground roll or takeoff ground run. The takeoff distance is from the point where the aircraft was stationary, speed was 0, till the point on the ground where it clears the obstacle height. That is the takeoff distance. So, takeoff run and takeoff distance are two different parameters. The takeoff distance includes takeoff run plus the air distance consisting of transition and climb to the obstacle height. Similarly, when an aircraft comes into land, the landing distance is defined as the distance from the point where the aircraft is at the screen height to the point where the aircraft comes to rest. This includes the glide and then the flare and then the ground run. So, at this point the wheels are touching the ground. So, from this point to this stop, it is the ground run. Now, the screen height is generally taken as 50 feet for transport aircraft, just like the obstacle height of 50 feet. For military aircraft, these numbers can change, they can be 35 feet, and the ground run is also sometimes called as the landing run. So, the contrast between landing run and landing distance is that the landing distance includes the air time in the air, in the flare, and the landing run or the ground run is only when the aircraft wheels have hit the ground and to a point where they come to a stop. Therefore, landing run is going to be always less than the landing distance, just like the takeoff run is going to be always less than the takeoff distance. So, there are basically 4 declared distances. The one is called as TORA or the takeoff run available. The next is called as the TODA or the takeoff distance available. So, you can make out takeoff run available is the distance available on the ground from start to the point where the aircraft leaves the ground, and takeoff distance available is the distance from the start of the takeoff to the point where the obstacle height is cleared. Similarly, you have something called as a accelerate stop distance available, which is that when you are planning to take off with a multi-engined aircraft, you might have a situation where you need to abort the takeoff and therefore, you will accelerate, but then you will apply brakes and stop because of some issue and you will come to rest on the runway itself. That is called as the accelerate stop distance available or ASDA. And finally, we have the landing distance available, that is the total distance available including the screen height or the obstacle height to the point where the aircraft comes to rest. So, now we will look at these 4 distances, how they are defined and what do they represent. So, first we will look at TORA and TODA. TORA stands for takeoff run available, the length of the runway declared available and suitable for the ground run of an aircraft during takeoff. So, during takeoff, the aircraft is in a ground run from 0 speed to the liftoff speed, and the length of runway available and suitable for the ground run of the aircraft during takeoff is the takeoff run available. The TODA or the takeoff distance available, on the other hand, it will be TORA plus some other length which is required for clearing the obstacle height. So, it is the length of the takeoff runway available plus the length of the clear way. So, now there is a new term called as a clear way. So, let us define what is meant by a clear way. So, clear way is basically an area which is clear of obstacles beyond the paved runway or at the end of the paved runway, and this is basically unprepared and could even be over water. So, as long as the airport authority has complete control on what comes up in this area and they can exercise control on not allowing anything that is not needed except for by function. So, the clearway is clear of all obstacles except those items which are required by function, like say the taxiway lights, runway lights. Okay. But as I said, it could be even an area over water which is clear of obstacles. The purpose of a clearway is to reduce the initial climb performances restriction. In other words, if we insist that the aircraft should obtain the obstacle height at the end of the runway, then a large distance called as the air distance will unnecessarily be a part of the paved runway, which is not really needed, because the paved runway is needed only for the takeoff run available. Okay, because during takeoff run the aircraft is still on the ground. At the end of takeoff run the aircraft has left the ground or has just left the ground. So, you do not have to necessarily have the runway below it available, it should just be clear of all obstacles, and that is why it is a clearway. So, the sketch here shows runway 0927 aligned 90 degrees and 270 degrees, and you can see that this is the threshold point for arrivals at this side, and this is the threshold point for arrivals at this side. So, for runway 09, at the end of the runway there is some area called as a clearway. You can notice that clearway is wider than the runway. Okay. Now, then we go now to the definition of LDA and ASDA. LDA stands for the landing distance available, that is the runway length declared available and suitable for ground run of an airplane at landing. So, after touchdown the aircraft has to be decelerated to a complete stop using reverse thrust, using brakes or whatever means, spoilers or air brakes, parachutes, whatever. Parachutes are not normally used in transport aircraft, but we do use spoilers, we do use brakes. So, whatever distance is available and suitable for aircraft for ground run is called as the LDA, and then the accelerate stop distance or ASDA basically is the length of the takeoff runway available plus the length of the stopway. So, now we have introduced a new concept called stopway. So, let us understand the meaning of that. Stopway is basically an area beyond the actual runway that is available to stop the aircraft in case of a rejected takeoff. So, once again, at the end 27 of the 0927 runway, when you come from 09 and you want to do a takeoff, you accelerate from starting point and then somewhere down the line you suppose for whatever reason you decide to decelerate or stop or abort the takeoff. Then you might be exceeding the runway, but there will be a stopway marked here by these yellow colored hash lines. So, this will be an area within the boundary of the airport under the direct control of the airport authorities, which allows the aircraft to be stopped, right. So, it has to be at least as wide as the actual runway and it should be centered to the runway center line. In this case, the width of the stopway is equal to the width of the runway, but it can also be more, it cannot be less, it has to be more. And also a stopway is expected to support the aircraft, to be able to support the aircraft weight during takeoff, and normally it is identified in the maps by large yellow covering stripes. Okay. There is one more concept which we need to understand when we declare the airport lengths, and that is the displace threshold. Now, threshold is normally the point where the pilot is supposed to aim for touchdown of the aircraft. So, it is marked by these zebra crossing type white colored lines, but in some cases Although the airport can handle the landing even at this point, because there is a proper constrained runway, because of some obstacle limitations there will be a control on the angle at which you arrive, and within that angle, if you are arriving within that angle and if you still are not able to clear the obstacles on the way, because there is a high altitude building or a high altitude structure in the approach path. So, therefore, you need to approach from above that, and so your angle of approach will be much larger. So, to avoid the danger of approaching at very high angle, what is done is the threshold or the aim point is displaced from this location to this location, and this information is communicated to the pilot using manuals, but you can also see these two arrows, the two white arrows on the airport. In all airports, wherever you have a displaced threshold, if it is substantial in length, then we normally put white arrows indicating the direction at which you are supposed to land, and also it is important to note that the threshold here is displaced. So, this much runway length. So, although runway is there, it can take all the loads, it can also allow you to do a takeoff, but because you are forced to displace the threshold, therefore, you will be asking the aircraft to be aligned here and then go for takeoff, right. So, this is an example of the original runway with a stopway. You could have a displaced threshold like this with stopway after that, or you may try to put a displaced threshold also within the stopway. So, the displaced threshold is the portion of the runway that starts before the runway threshold. It is available for takeoff, but not for landing. So, because when you want to land from this end of the runway, you can actually bring your aircraft here and then use this distance also for your takeoff, because it is classified for, or it is approved for aircraft rolling as well as aircraft impact at landing, but not for landing. So, this distance is available in this direction for takeoff, but not for landing. And in the charts that the crew members carry on board, such areas are identified by these white big arrows on the actual runway threshold. So, let us look at an example of various combinations of takeoff run available, takeoff distance available, accelerated stop distance available, and the landing distance available, depending on the various circumstances, presence of stopway, presence of clearway, presence of both stopway, both clearway, etc., etc. So, in this example, please assume that all flight operations take from my left to the right as shown in the arrow. So, the first is a most trivial case where we do not have any clearway nor any stopway at any of the two ends. So, therefore, assuming operations from left to right, in this case there is a pavement. So, the takeoff run available is equal to the takeoff distance available, is equal to the accelerated stop distance available, is equal to the landing distance available. So, that is a simplistic solution when you have no clearway and no stopway. If on the other hand you have a clearway, then the takeoff run available, the accelerated stop distance available and the landing distance available are the same. You are supposed to finish everything before the runway, but for takeoff distance available, you have now an additional area which allows you to utilize it for flying in the sky. So, you are still on the home territory, but you are up in the sky. So, that is what it is in this case. Now, many pilots do not like this system of only one type of field, whether it is runway, taxiway or any other field, they do not want it to be almost the same type. So, there is one more example in which there is a clearway created here. So, this clearway, is it meant for the safety of the people from right to the left or from the safety of the people who are from left to the right? So, obviously, this is meant for people. See, takeoff will take place only from left to right. So, what will happen is, If you have a clearway, then the takeoff distance available becomes beneficial, because from here to here anyway you require, because of takeoff distance available, remaining portion is available only for takeoff distance. So, therefore, presence of a clearway can improve the value of the TODA of an aircraft. Let us look at one more example. In this example, we have a stopway, okay. There is no clearway, but there is only a single runway and there is a desired trade off. Okay. So, what will happen here is that if you start from here, you have TORA, ASDA and TODA available for the aircraft. Okay. Let us take another case where both the clearway and the stopway are available and the threshold is also displaced. Okay. So, you can see this is the displaced threshold. So, therefore, in this direction the landing distance available will be directly equal to only the pavement which is available minus the stopway minus the clearway, because stopway and clearway can be used only during takeoff. During landing you cannot take advantage of stopway or the clearway. So, the takeoff run available will be from the starting point to the point where the stopway starts, because you need to clear the airport obstacle height before you come over the stopway. For accelerated stop distance or ASDA, from the starting of the airline, from the starting of the air runway to the point where the stopway ends, we can have the accelerated stop distance, because the stopway can take the load due to the aircraft's ground acceleration, and the TODA or the takeoff distance available will be the TORA plus the clearway. One more thing I have observed is, I will talk about it later when we come to that point. Now, let us look at an interesting aspect related to the various special speeds, or we also call them as V speeds. During takeoff there are many speeds called as V speeds. So, we will look at it one by one. So, friends, Vs is the stalling speed or the 1g level stalling speed. This is the minimum speed at which the aircraft can generate lift equal to weight. So, below this speed definitely the aircraft is heavier than air and it has no net lift acting on it. V1 is the name given to a decision speed, because when you reach speed V1, you have to make a decision whether to continue with the takeoff because everything is going fine, or abort the takeoff, because you know that one engine has failed. So, you are on the power of the remaining engines, and the remaining engines should now be able to give enough power so that you can achieve the required speeds. Then we have the speed called as VMCG, which stands for minimum control speed at ground. Now, do not confuse with the previous slide, that was for some other aircraft type, this is for some other aircraft type, but it is the same thing basically, that it is basically the minimum speed at which the aircraft can be controlled when on ground. During the ground roll itself you need to control the aircraft, because if there is a rudder untrimmed, it will take the aircraft in one direction laterally. If there are other CG problems, there can be a requirement to bring the aircraft back, because the imbalance cannot be handled by normal forces given by the pilot. So, there is a speed called as VMCG, which is the minimum control speed. Obviously, it has to be more than Vstall, but it can be a reasonably small number. It is mainly driven by the propulsion considerations, availability of suitable energy source or power plant meeting the low speed requirement. The next is minimum control speed, but this time it is in the air, because once you get out of the ambit of the initial ground motion of the aircraft and you achieve a climb, there are certain minimum speeds which have to be maintained while going into a climb. Otherwise, you can be a danger to your own life as well as life of the others. Okay. So, there is some minimum control in air, which means when the aircraft has got one landing gear leg on any part of the world, it normally requests its sponsors or organizers or to permission to you go for last mile delivery. Now, we notice that there are minimum control speed on ground and in air. What does it mean? So, here is an example of the definition of VMCG and VMCA, which stands for minimum air control. This has never happened in the past. We have never had any query like this, but it is okay, we will clarify the queries. So, VMCG stands for how much distance offset does a couple travel using its landing gear for minor aircraft. So, you can see that on the ground the blast of the jet engine or any disturbance can lead to an error of around 30 meters here. Okay. Now, in this case it has been seen that engine fails before the minimum ground control speed, then do whatever you want. Actually, it will be stupid on your side to continue with takeoff, because after 2-3 years you are lucky to get a seat in that quota. So, you will be made redundant very soon, because you have to be current. So, if the engine fails before VMCG, you must abort the takeoff. If you are a multi-engine aircraft with more than one engine, suppose you have two engines for example, and if one engine conks off, you are left with half the engine power. With half the engine power, you really cannot run the aircraft to its full flight envelope. So, you will have to do certain maneuvers and then you have to come back and report that the aircraft is okay. So, on the ground, the place where your aircraft is drifted by the aircraft ahead of you, if you are able to move around 36 inches in the nose with 45-degree payload, you are liable for this particular payment. Okay. So, VEF, or the equivalent flight speed, is greater than the equivalent speed QA. Then we also have what is called as VMC air, that is how much is the controllability of the aircraft when it is in the air. So, for VMC there is a requirement that the value V2, which I have not discussed so far, the safety speed, it should be more than 1.1 times VMCA, and it should be also 1.2 times the Vstall. So, going back, we have seen VMCG and we have seen VMC. Now, there is something called as V rotation or VR. This is the minimum speed at which, if the pilot introduces nose up pitching moment by deflecting the tail up, the aircraft should start rotating on the main wheel, and then subsequently it should be able to lift off. So, the speed at which the speed corresponding to the speed at which rotation is initiated is called as the rotation speed. Then the minimum unstick speed is the minimum speed at which you can leave the aircraft and make it climb on its own. In some cases, to know the performance of the aircraft in the minds of the people who are using it, pilots are asked to give a feedback on the situation of takeoff, and they get an idea about the lift off speed by looking at the charts, because all these things happen in a matter of few minutes. So, keeping a detailed chart on the current situation is not easy. So, therefore, there are regulations which require you to report yourself to a police designated police officer and then explain the situation and get a clearance from them. Only then you can talk to the media and you can open up about this. And finally, we have the takeoff safety speed V2, which is nothing but mandated as 1.3 times V star. 8 Kohli and the other players like KL Rahul. Okay. So, that is V2, the takeoff safety speed. The speed at the end of V2, we assume or we say that the takeoff has taken place properly. Now, the question that is answered when we look at the runway charts is, how does one determine whether a particular aircraft can operate from a particular runway at a particular airport. How do you do that? So, for that we have tried to get some interesting material for you. So, we looked at the Federal Aviation Regulation, which are the FAA regulations. FAR 25 is applicable for ongoing business jets and GEON jets. So, all of you who are not businessmen, not genius jets, not retired, you will be allowed to complimentarily attend this particular seminar, which is happening on the 75th year celebration of our society, the Aeronautical Society of India. The Aeronautical Society of India. Okay, it is happening on 18th and 19th of November 2023 at a place called Yasho Bhumi in New Delhi. Locality is called Dwarka. So, for turboprop and turbofan powered engines, here are the guidelines. Okay. These guidelines look at 3 cases. It look at the runway configuration, gills configuration, and the layout by the current author. So, to determine the correct runway length required for safe operations, as I mentioned, you have to do 3 calculations. One of them is to estimate the volumes. One way is to estimate the full strength pavement or FS required for a normal takeoff when all engines are available. The second option is to do it based on the data regarding takeoff involving engine failure, as I mentioned to you, the accelerated stop distance, or in this it depends upon decision making, whether decision is taken at takeoff or after takeoff. The next operation is landing. In landing, we know landing basically means coming down at an angle and speed which is safe for you to operate. There is a limit to the touchdown speed, and then you put the pressurization system, and then if it is there. Now, let us look at the nomenclature for what follows in the next few slides. So, FL will be called as the full strength or full field length, total amount of runway length required. FS is the full strength pavement, as I was telling you. Clearway distance is called CL, stopway is called SW, takeoff run is called as TO run. Then we have takeoff distance. So, we have this liftoff distance, takeoff run, landing distance, stopping distance, and D35, which is the distance to clear the obstacle height of 11 meters or 35 feet. So, let us look at them one by one, the 3 cases. The first is the landing case. In the landing case, the aircraft approaches a runway and aligns itself with the runway center line, hopefully riding on those markers, outer, middle, inner markers, and as soon as it reaches the obstacle height of 15 meters, the initiation of takeoff is said to have started. So, you land, you brake, and you catch hold of a few circles like me to look at the graphs. Okay. So, from where you came in to touch the ground to the stop point. So, here is the landing case with more accuracy. So, here you have the 50 meter or 50 feet obstacle height, and the stopping distance that aircraft comes and waits, actually it does not stop here, it goes slightly more, but let us say it stops at this point. The distance from obstacle height beginning to the end of this is called as the takeoff distance. Now, there is a requirement that the distance to stop must be 60% of the distance of landing. So, landing distance is from the obstacle height to the end, where the obstacle comes to an end. Okay, it has got the person has got extremely high, large number of this can be deleted, it is not important. So, the distance to stop must be 60% of the landing distance. That means, if you look at the parameters that you will get out of this particular exercise, you will get the stopping distance and the landing distance, which are both the same in this case. So, it is important that anyone who restricts our student in the class or threatens to take it against them should not get affected and should say that I am going to report minimum as per the triangle, but you will export more. So, in this case what we see is the landing distance must be the full strength pavement Fs, because there is no scope to reduce anything here in takeoff. So, let us take a normal takeoff case. So, in normal takeoff case, the aircraft achieves the liftoff distance, then climbs and reaches the obstacle height of 11 meters or 35 feet. So, the distance from starting point to the point where you have 35 feet obstacle height clearance is called as D35. The liftoff distance will be from starting point to the place where the aircraft lifts off, and you multiply the landing distance with 115%. The liftoff distance, sorry, not landing here, the liftoff distance is multiplied by 15% more to take care of the differences in the pilot's flight frequencies. So, the takeoff distance will be 35 feet plus 11.5 feet, and then you have a clearway. So, there is a restriction on how much clearway you can build. It has to be less than half of either the takeoff distance or and minus 15% of landing distance. So, landing distance into 1.15 into 0.1 to be subtracted from the takeoff distance. Half of it is given to each subway on both the ends. So, that is how they get the area. If this area goes negative or below 0 or below 0, it means we have a crisis. We do not have enough money to pay for the uniforms of our bureaucratic system. Okay. Another information is that the clearway less than half of TOD minus 1.15 LOD and the takeoff run will be TOD minus CW, which is fine. So, the full strength runway that is required will be equal to the takeoff run from here to the place where the aircraft takes off. Now, let us look at the engine failure case. In case of a single engine aircraft, all these things do not apply. In case there is a single engine aircraft and it fails during any phase of flight, maybe takeoff, maybe climb, the safest thing to do is to come back to the origin, unless you are very far away. Okay. So, there is a speed called as the decision speed V1. This speed is communicated by the manufacturer to the airline, and it is a function of many parameters. It is a function of natural occurrence of some items. So, let us see a standard case of engine failure. The aircraft has accelerated and suddenly for some reason at this point it realizes that it does not want to continue with takeoff. So, he detects engine failure at this speed V. So, we are looking at a typical engine failure case. We are looking at a typical engine failure case where the aircraft starts its takeoff run and at some point it accelerates to a speed, and at that point there is an engine failure detected. So, now the aircraft pilot has two options. One is either you go for an emergency stop or you continue the takeoff. Now, you will do an emergency stop if the engine failure is detected very much near the point where you would have achieved liftoff, and obviously if your engine failure is detected very much towards the end, you would continue with the takeoff, because it will be dangerous for you to abort the takeoff. You are sure to cross the runway and maybe cause damage to the runway boundaries. On the other hand, if you are at the beginning of the takeoff cycle and if the engine failure is detected, it will be better for you to go for an emergency stop. So, if V is less than V1, the engine failure at speed V, there is some speed V1 called decision speed. This is communicated to the pilot before each flight. It is a function of the weather, temperature, pressure, ambient conditions, aircraft center of gravity, fuel available, all that. So, there is a particular speed during takeoff which the pilots indicate or mark in their instrument. If the single engine failure of multiple engines or one engine failure out of multiple engines occurs at a speed less than V1, you should brake and stop. If it occurs at a speed higher than this speed V1, you have to continue your takeoff. It will be dangerous to stop. Okay. So, let us look at emergency stop. So, okay, the pilot observes that the value at which my aircraft has experienced one engine failure is much lower than V1. Therefore, they will decelerate and come to the stop, and for that you can exceed the runway and go on the stop way. So, that distance from start to accelerate till the engine failure speed and then to decelerate is called as the accelerate stop distance, or called as DAS in this particular slide. On the other hand, if you continue takeoff, then you are going to accelerate slowly, because now one engine is not working. So, the speed at which you will achieve the lift off is going to be higher than normal condition. In the climb also you will be climbing little bit slowly, and therefore, you will be able to clear the obstacle height at some distance. That some distance can be over the clearway. So, that is called as D35, that is takeoff distance to 35 feet with one engine in operational. Okay. Now, here there is no percentage applied because it is an all engine takeoff case. So, here the parameters which come into play is the takeoff distance D35, the lift off distance, the clearway, the stop way and the landing distance. What we obtain is the decelerate to stop distance, the lift off distance and the stop way. Now, there is an idea of balanced takeoff with one engine in operative, and that is a condition when the accelerate stop distance with one engine in operational is equal to the total distance required to clear the obstacle height with one engine not working. So, when both of these are equal, that particular length is called as the balance field length. Okay. So, for runways with no stopways and clearways, the balance field length tends to come up with an efficient runway length. That is the minimum runway length required for safe operation. Why? Because if V1 is low, then aircraft can easily stop, but it will not accelerate fast enough to reach V2. If V1 is high, then it is not going to stop, not long enough runway available to stop if needed. So, if you have a situation that the one engine in operational accelerate stop distance is equal to the one engine in operational takeoff run till 35 feet, then it will be called as a balance field length or balance field takeoff distance. When both the stopway and clearway are present, then ASDA or TODA will be more than the physical runway length, okay, because it is not ideal now, because both are available. So, therefore, you do not have to worry about finishing your takeoff within that. So, if stopway is present, V1 can be more than the balance V1. Okay. So, there is also a concept of negative stopway. So, regulations require that there should be at least 1000 feet of runway safety area present past the last bit of the usable pavement. So, at the end of the usable pavement, that is the runway, the constructed runway, there should be at least 100 feet available for safety area. Now, this particular distance could be less than 100,000 feet if you use the EMAS systems, but this is a very expensive system. So, many airports are not able to either create this runway safety area of 1000 feet or install an EMS system at every runway end. In these cases, the FAA allows pilots one of the following two options. One is you physically reduce the runway length that is available until an adequate runway safety area is present. So, what you do is you sacrifice a part of your runway length to meet the requirements of the runway safety zone. So, you can say that some part of the runway is not available to you because it has gone to create a safety zone. The other option is that you reduce the declared ASDA and or LDA. You do not allow the pilots to use the entire runway. So, we will look at an example of an airport in Florida in USA called as the Naples Airport. As you can see, it is almost at the bottom of the Florida between Miami and Tampa. A closer look is, you can see this is where the airport is located. It is a cross runway, and you can see that there are lots and lots of construction activity, construction and other things at the ends of the runway. Now, let us focus on this. So, this is how it looks like. Now, if you look at the airport chart for the Naples, Florida runway 14, you will see that the runway length that is available 1432 is actually 5000 feet. That much runway length is available. However, there is a road 450 feet beyond the runway end. So, from the runway end to this point is 450 feet, okay, and there will be traffic in this area. So, you cannot assume it to be clear, it does not be a part of the clear way. Unfortunately, there is no land available for us to have 1000 feet gap. So, the accelerate stop distance is only 4550 feet. So, when you come in from here, you will have to accelerate and stop in 4550 feet, because 1000 feet clearance is required. So, 450 feet is beyond the runway, and another 450 feet, 550 feet is consumed. So, you have ASDA of 4550. There is no clear way or no stop way here, therefore, ASDA and TODA will not be the same. Okay. Now, there is also a displaced threshold of 128 to 130 feet. So, therefore, the landing distance available is going to be less than ASDA. For ASDA, you can start from the end of the runway and you can come to the stop, but because there is a displaced threshold, some portion 130 odd feet of runway is not available for the landing. So, therefore, the LDA is going to be SDA minus 128, it becomes 4420 approximately. So, the TORA and TODA are 5000 feet for runway 1432, ASDA is 4550 feet because of the presence of this anomaly here, that there is a road and at the end of the runway there is only 450 meters available, and LDA is 4420 because in LDA there is also a displaced threshold of 130 feet approximately. Okay. Now, the runway length required by an aircraft changes with the airport elevation, with the temperature at the airport compared to the ambient conditions, and also the slope or the gradient of the runway. So, we have to apply corrections to these, and the corrections have to be applied in this particular order. So, under standard atmosphere, the temperature at the mean sea level is 15 degrees centigrade or 288.16 degrees Fahrenheit. The pressure at the mean sea level will be the 760 millimeters of mercury or 1.0315 bars, and the air density will be 1.2256 kg per cubic meter under standard ISA conditions. Right. Now, unfortunately, all runways are not at mean sea level, they are not on perfectly level ground, they are also not having the same standard temperature and pressure, it can change over the years. So, how can we determine the correct values to be specified? So, let us look at the corrections. So, you do elevation correction, then you do temperature correction, then you do gradient corrections, and you go in this order: first elevation correction, then temperature and then gradient. So, let us first see the elevation correction, how it is brought about. So, here is an airport and it is right now shown as mean sea level, but actually speaking this aircraft actually is now at a height h. Okay. So, this runway is not available at sea level, actually it is at some height. So, there will be a basic runway length due to elevation, which will be different from the basic runway length at the standard sea level conditions. So, how do you apply the elevation correction? Well, you look at delta t by delta h. So, the change in the temperature because of altitude is 6.5 centimeter per kilometer to 11 kilometers, and then it is constant to 20 kilometers, and then it is increasing by 1 degree per kilometer at 20 to 32 kilometers. This is the ISA data. So, what we do is we look at the ambient pressure temperature differential, we look at air density, and we also look at other factors, but all in all we say that for every 300 meters rise above mean sea level, add 7% to the takeoff distance. So, if the takeoff distance under ISA conditions at sea level is 1000, it will become 1070 when you go to 100 meters above mean sea level, because there will be a 7% rise for, sorry, if it goes to 300 meters, it will be 1070. Okay. So, how do you calculate the effect of temperature? So, there is a runway which is at standard value of whatever is there in the ISA for the altitude. So, it is a basic runway length BRL, but when your temperature changes to high temperature, there is going to be higher value of BRL. It will not be BRL, it will be BRL T, where you are showing here that effect of local temperature has been considered. So, how do you apply the correction? So, the standard temperature at mean sea level is 15 degrees centigrade. Calculate the standard temperature at an elevation in degrees centigrade, suppose it is 10 degrees. Then apply this formula to get the airport reference atmosphere, T as mean sea L. So, based on the elevation of the depth of the runway, there is going to be a standard temperature at elevation, which will be T at mean sea level, which would be there at this condition, plus half plus delta T by delta Z into Z, where is the elevation. Temperature is normally taken as the temperature recorded T1 plus difference in the maximum and minimum divided by 3. Okay. So, T1 is the monthly mean of average daily temperature for hottest month of the year. Monthly mean of the average daily temperature taken in the hottest month of the year, that is T1. T2 is the monthly mean of the maximum temperature of the same month. Okay. So, basically T2 minus T1 upon T1 for 3 months. Correction here. So, 1% rise in the takeoff length is expected for 1 degree rise in the ART, corresponding to, apply this at elevation of BS, sorry, once again. So, 1% increase in runway length has to be added for every 1 degree centigrade rise in the ambient in the airport reference temperature above standard. Now, what does ICAO recommend? ICAO says that the total correction elevator and temperature, that is corrected length minus initial length upon initial length, it should be only up to 0.35. That means 35% extension is permitted. Okay. If it is a case that you are getting a larger variation or a larger one, that means you are at very high altitude and also very high ambient temperature, then you have to do actual testing and not this particular model calculations. Okay. So, the bottom line is, for every 1 degree change up to 300 meters altitude, you will lose 1% of your altitude. Now, runways are constructed by humans and they are not perfectly flat. As you can see in this side view of this runway is not flat. It has lots of ups and downs or gradient. So, how do you incorporate the gradient correction? So, we have to understand first what is meant by this gradient. So, it could be transverse gradient or it could be for quick removal of water, or it could be longitudinal gradient for better performance. But if the gradient is too steep, then you have a premature lift off and structural defects. Okay. Lower gradient will cause higher consumption of energy, hence longer runway. So, you got to choose between the two options. So, one of the common strategies is runway elevation max minus min, that means the runway height above the mean sea level multiplied by TOW, RW and length. So, in short, the correction for gradient is 20% for every 1% increase in the ELG. So, all three together. So, here is an example just to test your knowledge. So, the basic runway length BRL is given as 1600 meters. The airport is at 125 meters height, it is a very high location. Calculate the basic runway length for following things. So, what they have done is, they have measured the numbers at various times of the day and they are trying to show it to us just for us to check. But first we will give you the value that we expect. Okay. So, if the basic runway length is 600 meters, you have a wing of 125 meter wingspan. The ambient air temperature is also very hot. So, first you apply correction for elevation. So, here is an example of an airport which has got a basic reference length of 1600 meters. It is an airport of 125 meters above mean sea level and the average temperature is 25 degrees centigrade. So, one is we correct for elevation. So, 7% per 300 meters rise and the rise is 125 meters. So, basically it will be the basic number 1600 into 7 by 100 and into 125 by 300, because in 300 it should be 7. Therefore, how much will it be in 135 can be calculated like this. You get 46.67, that means the runway length will be 1600 plus 46.67, 46.67. This is now only for the first correction, we are not done yet. Now, this 1646.47 becomes now available to you as an information. Now, you apply the corrections for temperature. So, again the Maratha warriors had the same thing when they looked at the temperature. So, at 125 elevation, the temperature expected is 15 degrees minus 0.0065 into 125, which is the lapse rate. It is 14.19 degrees centigrade and ART is 25 centigrade. That means, the delta T is basically 10.81 centigrade. In other words, when this aircraft went to a height of 135 feet above mean sea level airport and also observed temperature 25 degrees centigrade, it is 10.8 degrees centigrade more than the recommended value. Okay. Now, 1% per 1 degree rise in ART from STE. So, 219 is the maximum number of ARTs given, minus 1% into. So, this number came from the correction applied previously. 1% of this into 10.81 will be the value. This is the increase in the elevation because of the slope, 1 centimeter. So, the corrected length will be 1646.7 plus this, it is 1824.72 meters. Now, we have to check that this total value is not exceeding by 35%. So, we look at what is the total correction applied, divide by the original number. This comes to be 14.4%, which is way below 35%. There was some controversy here, but finally we just got to know that the other student was lying. So, here if you see, the temperatures are conducive to reduction. Lastly, we look at the corrections due to the gradient. These gradient information is fed through what are called as gradient charts, which have a long list containing the limits, the global granted, and to the rise and fall all of them in percentage. So, we will go through quickly. So, imagine a runway of length 0 to 2100 feet. From 0 to 300, it has a gradient of +1. So, there will be a rise of around 3 meters. Then next day we throw the shakil to Khan. So, let us assume that the first 300 meters you have a gradient of maximum 3. For the next 300 meters you have -0.2, next 300 meters you have 4.8, next 300 meters you have 7.8, and next you have again 6.9. If this is the case because of the gradient, then let us see the correction. So, the effective long gradient will be runway elevation minus runway elevation divided by tower total runway height width. So, the largest number was BRET 18,1824.72. So, ELG will be 7.8, which is the number for the highest value, minus 0. So, basically we are asking the mountains to choose a person from place from where, because of your own background, you can claim to get more benefit. So, ELG in this case will be 7.8 minus 0, because 0 is here and 7.8 is here, maximum minus minimum divided by the length, it comes to be only 0.43%. So, we need one gradient for 200% for every one. So, we already have taken care of that. So, the BRL ETG is coming to be equal to BRL ET plus LG. Okay. This number 146.93 which has come from the correction by multiplying your own volume with other people's volume. Sorry, we will have to repeat that correction. So, the correction is coming based on the gradient. It is 1824.72 which we got earlier for the temperature for the altitude correction and temperature correction together, and then you add to that 156.93 meters because of the gradient. So, the final answer is 1981.63. So, if you look at any chart, you will find takeoff run available, takeoff distance available, accelerator stop distance available, landing distance available, mentioned for all the airports, and in some cases you can see threshold displayed by some 65 meters or 160 meters. Okay. So, this is how the charts are indicated. You can see the numbers here given in the chart. Similarly, if you want to look at some other airport, there is a source from the aviation information publication in India, where all airports in India the data is available. What is the TORA, TODA, ASDA and LDA, etc. Okay, so you can see this. For every airport, some charts are available which will help you achieve the knowledge. Okay. Thanks a lot for your attention.